Martin Rowe with EE World. We are in San Diego at the International Microwave Symposium, and this is the Rohde Schwarz booth, and we have Harold Spector here with us, who is going to explain these power amplifiers and why you want to make sure that you get the most power, but not too much, because if you get too much, you won't be in the linear range, and then you'll have all kinds of problems. So Harold, why don't you explain why we want to get the power just right?
Thank you very much for having this talk with you, Martin. The setup which we see here, this is a setup which typically is being used for EVM measurements. EVM is very important in 5G communication.
Yes, it is. Error vector magnitude.
That's correct. That's what we are talking about. And typically you face the situation when the signal generator cannot provide you sufficient power, linear power, in order to do a good transmission of a 5G signal, for example. We are talking typically about 1% EVM values, which is a good measure that you can transmit in an excellent way a 5G signal. So when the amplifier comes into saturation and you don't have the power, the question is, how can you measure components which need much more power, for example, power amplifiers or mixers or filter? How can you generate this high quality signals? You can do this by choosing an appropriate amplifier to do that. But of course, guys who are in the amplifier business will know that EVM will be deteriorated if you add additional amplifier into the signal chain. And this is where this setup comes into place. We wanted to show the people here on this Genius booth how they actually could measure the performance of a complete setup consisting of a signal generator, an amplifier, and last but not least, the analyzer. So this is a vector analyzer, which shows you then actually the real EVM over the complete signal chain. So this is basically the challenge what we talk about here.
Okay. So can you explain some of these bar graphs? What is that telling us?
What I will just tell this one. We have here the setup. You see here, this is a SMW 200A, which is a high performance signal generator. This is feeding here the analyzer, so it's a straightforward through into the signal generator. So we measure here the reference EVM, what the signal generator is capable to do. So we see here it's at a high, it's 0.3%, which is extraordinary, perfect signal, basically. So we have here the reference. And the challenge will be then, if I take this signal into the amplifier and then measure the output of the amplifier. So this is what we show here. And you see then what EVM value is being contributed by the amplifier. This is what we do here.
Okay. What kind of frequency are we running here?
This is from 2 to 20 gigahertz, capable to do that. So this is a very robust, basically a gain block, a very new product of Rohde and Schwarz in this frequency range. However, in this case, we are going at 4.9 gigahertz. We just choose a random frequency in the frequency range, which is being capable to handle by this amplifier. And when we do this test, we realize that with this setup, you can generate about 35 dBm with this generator, which still might be too low. And then is when the big guy, the big brother comes into place. This is an amplifier from 380 megahertz to 6 gigahertz with a nominal power of 180 watts. So this gives you much more headroom and therefore will give you a better performance EVM-wise than compared to this one. And this is what we do as a part of Genius test here to make the audience aware how to balance a good trade-off between signal generator and the amplifier in order to get the best performance, for example, for your RF component testing.